Hello, folks. Welcome to Rational Science. We got a great day today. I hope I can get through all the material. We're going to be talking about light. Does light travel straight always, or does it curve? I mean, when you're not drinking, okay? Does light curve? General relativity holds that light is bent or warped, or it's like a banana in some cases, just turns a corner. Is that so? Does it curve? Does it travel curvilinearly? That's the question. But before we get there, I got a couple more issues that have come up, and I just want to clarify them a little bit because people are very much mistaken on certain things. And here are a couple of notions, irrational notions that people have. One is that they believe that air and water don't have shape. Very common. A lot of people have brought this up to me. No, air doesn't have shape. Water doesn't have shape. It takes the shape of the container or whatever they come up with. These are kind of answers I get. And the other one is that a lot of people say, well, space is completely filled. It's entirely filled. There's no space left. Okay, so, well, I'd like to answer these two because it shows that a lot of people are having problems with basic stuff, with simple baby kindergarten stuff. And that's the way I look at it. And they're not the only ones, this has been around for centuries. The notion that, there is no such thing as space. There's every bit of space is filled with something. That's the notion they have. Okay, so here you have a little bit of history on that. Okay, Parmenides was one of the first to say there's no such thing as void or empty space. All of space is filled with what? Being. Okay, not beans, but being. Okay, what does he mean by that? Well, he thought that was a single, indivisible, unchanging reality. So being is reality, reality is being. Great, we learned a lot. But he said, what is not cannot exist. Only what is can exist. That's kind of like the definition of exist and reality. What is, right? What do we mean by that? Yeah, and he says it's being. So he just ran around in circles because he never defined the word exist or word being in a rational manner. That's the whole thing. But he said being is indivisible and unchanging. And a multitude of things we experience is just an illusion. That was his notion 500 years before Christ. Yeah, I guess being the first attempt or one of the first attempts, I guess you can forgive him, right? A few centuries later, we have René Descartes, and he says, empty space or vacuum does not exist. Space is extension. It's extension. An inherent property of matter. Matter is extended to a region where we cannot sense it. Okay? Empty space is insensible body. It lacks sensible qualities we associate with matter. That was his general notion of that. And in more modern times, 20th century, a fellow brought this up. He mentions Tesla, and he says the following. These are not Tesla's words. This is a visitor. Okay? It says, Tesla considered the ether as a dynamic, energetic medium thing, right? That filled all space and through which forces propagated. Well, assuming that was the notion that Tesla had, and I think it's pretty much the notion he had, it was an irrational notion to say that there's something, call it whatever, an energetic medium called ether that fills all of space. Well, where does space end? And what is outside of space? And that's where, they drop the ball and they say, oh, Bill, you're doing a word salad. That's where they never answer the question. The real question is, what is the shape of space? If space is filled, then space is some kind of container. And as far as I know, all containers can be, identified as objects. And that means you got to identify also the object or the thing, the whatever that gives it shape. the shape of the container. Anyways, the file continues, says, the electromagnetic ropes fill all space. And no, the answer is absolutely not. Okay? And here, let me show you why the ropes cannot fill all of space, and we do not say that here in this channel. Okay? So, no, the ropes do not fill all of space. Here you'll see why. Okay? There you have all the ropes connecting atoms everywhere, right? That's our hypothesis. We're saying any two atoms are interconnected, are bound to each other by electromagnetic ropes, not waves, not particles, but ropes. It's a pair of twined threads, DNA-like threads that binds any two atoms. But that's not the issue. The issue is, what's the black stuff? What do we call the black stuff that gives shape to all these little balls and ropes that interconnect them? I mean, if we were to remove all the black stuff, we would have a single entity, the block universe, essentially. That's what we would have. So, you got to tell me what the black stuff is. And you can't say it's space, because you're saying there's no such thing as space, which is what chisels the shape of anything in the universe. Every atom in the universe, everything that exists, had better have shape as a backdrop, giving it shape. Otherwise, if there is no such thing as shape, then we would have space. There would be a block universe. There would be a single block, I guess an infinite block, nothing on the outside of it, which is unimaginable, right? And nothing, no partition, no little pieces inside. It'd be a single piece, because nothing is there to chisel one object from another. So these notions that these people have is just, they're irrational. And here's another fellow, I talked about him the other day, and he said the following. He says, Gaede insists that space is an empty, passive void. Nothing, right? Modern physics has proven otherwise, okay? We have proof, fellows, okay? So take note. Gravitational lensing. Massive objects like galaxies bend space-time around them. Okay, so that's one of the proofs, evidences he points to, that space is something and we can bend it. Okay, that's what he's saying. Light from a distant object passing through this curved space-time will follow a bent path. I like the fact that he changes the wording, the official wording. The official wording is light is bent, and he's saying the path is bent. In other words, again, I talked about it a little bit the other day. We're talking about either the road or the car, right? And the official version is that the car is bent. The car is curved. And he's saying, no, it's the path, the street, the road. That's what's bent. And the car follows, curved or curvilinear trajectory, itinerary, because the road is bent, is curved, right? So those are two different things. And the official story is that the car is bent. Okay, they say light is bent, not the space. But they also say space-time is bent, obviously. But they always put it in those terms. Light is bent, light is warped. Okay, and that gravity warps light. And at that point, you wonder, what do you mean? The car is being bent, is warped. So keep those in mind. When they say those words, you got to keep that in focus. Don't let it go by, because they're cheating on you, okay? You got to ask them, what are you talking about? Which one? Are you talking about the road or the car, right? That's what you got to ask. Just as a marble would be stretched, wood on a stretched rubber sheet. In other words, this is the rubber sheets analogy. And the problem with that is that there is no such thing as the rubber sheet, because the so-called rubber sheet that he's talking about is a warped fishnet. And the warped fishnet is not an analogy for four warped number lines. That's what general relativity proposes, that the number lines are warped. It's a mathematical concept which they represent unjustifiably, right, with a fishnet, a warped fishnet. Doesn't have any fish in it. They usually put a planet in there, but that's what it is. Okay, it's 4 warped number lines. It says we observe this as gravitational lensing, where the image of a distant galaxy is distorted and magnified by a closer one. This effect has been confirmed countless times. He says he's got proof, evidence, right? The object doing the bending is what? Space-time itself. So now space-time is an object. Why did he put quotes on object? I mean, if it's an object, you shouldn't have to put quotes. Is space-time an object or not? Or is it an abstract concept? And yeah, it's an abstract concept, and you don't have to bend light. We're going to talk a little bit about that today. You don't have to bend light to make it curved or follow a curvilinear trajectory, meaning the photon deflected because the road, meaning space-time, was curved. Okay? And so all that is nonsense. The physical interpretation has no place in science. You can't say that space-time, which is 4 number lines, is warped, and that the little electron bead, or photon bead in this case, the photon bead, is deflected. It would like to go straight, but since the road is curved, it has a curvilinear trajectory or itinerary. Both are nonsense. First, light is not a little bead. That's the first problem, and we're going to talk about that today. And the other one is that, space-time cannot be curved because it's an abstract concept, mathematical concept for number lines. You don't warp number lines, not in physics, not in the physical world. I mean, it's an irrational physical interpretation, essentially. Okay, and so, we do define space in our foundations of physics. Those are the words you need to define to do physical interpretations, which is what physics is 150% about. We don't care about the math. We don't care about experiments. You come to the conference, you better explain something, and hopefully you explain give a physical interpretation for some phenomena out there. And the ones we are lacking on are light, gravity, magnetism, electricity, and the workings of the atom. Those are the ones, the invisible ones, those are the ones we're having trouble with. Okay, so there you have it. Space, that which doesn't have shape. It's a synonym of nothing, and it's the opposite, the antonym of something, which is what an object is. So something is that which has shape, nothing is that which doesn't. Very simple. It took 10,000 years for someone to come up with that definition. And people don't like it because it destroys their religion. They say, oh, hold it, Bill, where's my religion gone in the last 2 seconds, Yeah. And, okay, how about the second question? Or I think it was the first one, about water and air. Are those objects? Do those have shape? Because that's what an object is, that which has shape. And they say, well, no, because it's changing the shape constantly. What shape can it possibly have is it's changing its shape from 1 millisecond to the next millisecond or microsecond or whatever. Well, everything in the universe changes shape from gazillionth of a second to gazillionth of a second. Even you. I mean, even if you stand still, completely still, every atom in your body, every single atom in your body is moving with respect to Jupiter, because Jupiter doesn't stand still. So every atom in your body is changing its distance with respect to Jupiter. Just take your pick, one atom in Jupiter. Every atom in your body is changing its distance with respect to one atom in Jupiter. And if you change your distance, you're changing your location. If you change your location, hey, you've got motion. Motion is 2 or more locations of an object. In this case, the atoms in your body. So everything is moving in the universe. That means there are no objects because everything is changing its shape from microsecond to microsecond, picosecond to picosecond, whatever you want. You can chop it up as much as you want. So you can't say that because water moves and air moves constantly that it cannot have shape. Everything changes its shape. That's the first issue. But anything that is made of atoms in the universe had better have shape. There has to be a last atom somewhere around the periphery, the surface, of whatever object you're talking about. You're talking about an asteroid. It probably has a last atom somewhere, at the edge. I should be able to go in any direction and find the last atom of that object. And the same happens with a gas. If I'm within a gas, if I freeze it, I take a snapshot of it, right? But I'm allowed to move around and go to the last atom mentally, right? With God, right? We both go there and we find the last atom for that body of gas, and that is the shape of gas, if it's got a last atom somewhere in its periphery. And people don't understand it because they don't conceptualize these things. They say, let's go to the lab and find out if it has shape. You don't determine these things in the lab. It's a conceptual issue. Shape is a static concept. Hopefully, every object in the universe that is made of atoms has shape. And that's the only universal property of objects. But so what we do, we stop all motion by putting the what we call this tool, which is a very useful tool to get rid of motion and time. And time and motion are synthesized in several frames. Usually 2 frames is enough, but if that's not enough, we need a film strip. Okay, no problem. But all dynamic concepts, such as examples that you see at the bottom, they require more than 1 frame of the universal movie. Okay, and so this universal movie allows us to stop time, stop motion. We're there with God, just looking at a single frame in God's camera, right? He took a picture, he filmed something, but now we're concentrating on a single frame of God's movie, of Father Universe's movie, right? And in that single frame, you had better find only static concepts, and you see those above in the yellow region: object, distance, location, existence. Those 4 specifically belong to a single frame. And the question is whether you can put water or air in a single frame. Okay, can I take water and air and put it in a single frame of the universal movie? Let's find out. Okay, because some people seem to have problem conceptualizing these things, which should be baby stuff. You should have learned this in kindergarten. What are you doing? What are you doing as an adult questioning these things? Okay, so here it is. Here you have air. Okay, I hope you see the air. This is, I guess, our planet, right, rolling along. And there's kind of like a misty, whitish kind of thing, like a cloud enveloping the whole planet. And we call that air. We call that mist, that fog, whatever you want to call it. We call that air. It's moving too fast for you? Okay, so let's stop it. Here we have it. Okay, there you can see different layers of air around the Earth. So first question is, does air have shape? You say, well, I don't know, I can't see where it stops. Well, okay, let's stop it somewhere. There it is. Okay, now you see where it ends. The last atom is there where the red line is. Okay, is that good enough for you to conceptualize it? There has to be a last atom of air around the Earth. Okay, I don't know how far away it is. Maybe it's in the stratosphere. We don't care about that. It's a conceptual issue. There's got to be a last atom of air, and we'll call it O2. Obviously, there is a lot of junk up there. All kinds of chemicals. We'll just assume that air is completely clean, pure, just O2. Maybe some nitrogen in there, if you want to put it in there. There's got to be a last molecule of air out there. Could be oxygen, could be nitrogen, or whatever. Okay, so yeah, the air does have shape. And here's a, here we're going to put it in the universal movie. There you see it. Okay, so it is a static concept. Air has no, in the definition of air, there is no provision for motion. Okay, so air is a gas. Gas has no motion involved in the word gas. Okay, and gas is something you point to. Air is something that you just simply point to. You say air. Of course, you can't point to air because it's invisible for us, but this is a conceptual issue. If we could color code air, and around the Earth, and you're outside of that with God and you and my friend and everybody up there, drinking beer, we would say that's air there, that thing that's around the Earth. Okay, it's a shell. And here's a 3D version of that, more or less. You can see what I mean. You got the Earth and you got all these layers of air. It gets lighter the farther away you go. Um, let's get rid of the Earth because that bothers people. Say, well, because it takes the shape of the Earth and blah, blah, blah. Okay, let's get rid of the Earth. I got rid of the Earth. Okay, no more Earth, guys. So now you know. Okay, so yeah, we can see what air looks like. It's a shell, that encapsulates, the planet. That's what it is. And people really have a lot of problem conceptualizing these things. And so what I like to do, I didn't bring it here today so that we don't waste that much time in it, but you can imagine an astronaut filling a balloon with air, right? Taking it out there in the middle of nowhere, popping the balloon, and the air comes out. This blob of atoms comes out. And when it does, you take a snapshot of it. Of course, you got God's eyes, or maybe you color-coded it before you busted the balloon, no problem. You take a snapshot, all that green blob, that's called air. That's the shape of air at that moment in time, cross-section of time, a location. And it continues moving and dispersing, getting bigger and changing its shape. Yeah, no problem. It does change its shape. That's not the issue. The issue, does it have shape? And hopefully, if you talk about changing its shape, hopefully you're saying that it does have shape. You're admitting it. Okay, so please be careful with your language. Okay, what else can I say about air? You pop the balloon. There you have your blob of air, and that's the shape of air. And again, we change shape. I'm changing my shape every second. So am I not an object because I keep changing my shape? No, hopefully I have shape, and I'm changing my shape because an object is that which has shape. Okay, there was a fellow some couple thousand years ago. His name was Darius. He was the king of Persia. And every time he'd go out there to conquer some land, he first gave him a choice. He says, give us air and water. And that meant that, he was allowed to bring his troops into the earth part. And I said air, I meant earth and water. He was allowed to bring his troops onto the earth, onto the land, and the ships onto the water. Okay? Well, if you leave it up to these people, they say, well, we can give you earth, but we cannot give you water because water is not a physical object. Why isn't it a physical object? Because it doesn't have shape, and Bill says only that which has shape is an object. Okay? So yeah, this is good old Darius here, and when he went to see the Greeks, he'd go in there and say, earth and water. And the Greeks, I think they killed the people, the messenger. They killed the messengers. And then the war started. But yeah, these fellows would not be able to offer good old Darius the water part. They said, well, we can give you earth, but because we think that's a physical object, but we can't give you water. Okay, so here we have our good old astronaut, and he's going to show us that, yeah, you can indeed see the shape of water. So be very careful here now. He's going to take water in a balloon. He's going to pop the balloon, and the water is going to come out as a blob. Okay, so here it is. Okay, watch carefully. You can see the blob there. It's got shape. Okay, you see it up close. Okay, does that thing have shape? Well, you say, well, I don't know because it's moving from frame to frame. I can't determine. Okay, so let's stop the motion. Here's the astronaut and his blob of water. Okay, just a little drop, I guess, and hopefully you can see the shape of that water. Of course, you can see the shape of the astronaut. And here's a little bigger so that you don't strain your eyes. Does that have shape? That's water there, green water, right? Maybe I should have chosen some different type of water. Okay, does that have shape? And here we can also put it inside, the Universal movie in a static frame. We don't need two frames to watch water. We can see it in a single frame. Okay, and that's the key point, that if you can put it in a single frame, it is an object. Okay? Every atom of that blob, it has a last atom right at the edges somewhere. It's a thing. It's an object. So yeah, water does have shape, and does it change shape from frame to frame? Yeah, so do you. Here's the water again. Okay, I hope you can see how it's changing its shape. But let's freeze a frame. There we have it. Okay, nothing's moving now. Okay, that's God's camera. Nothing moves in His camera. One guy told me, well, but the electrons are moving in the photograph. Yeah, from frame to frame. You need a movie to watch that. Okay, and again, these people have never learned to conceptualize things which are so simple. That's why the universal movie is a great tool, because you force them to concentrate on a single frame. And you only have, You have static concepts in there. Like object is a static concept. You don't need to move anything to have an object. Shape, exist, distance, location, all those are static concepts. So, this is the definition of an object. It's not that which you can see or touch, and we're going to get into that today, especially the see part, okay? And an object is that which has shape, and it's the only universal property. All objects had better have shape. They might not be able to be seen, some cannot be touched. All objects have shape. Okay? So, not all objects are visible, not all objects are tangible. And that's what, really threw people off for so many centuries. They always thought that an object was a synonym of existence. In fact, David Hume and Immanuel Kant, they believed that they couldn't find any difference between an object and its existence. They said, what's the difference? An object is existence. And yeah, the difference is, again, they never define objects, so they would never figure it out. And they never define existence. But what existence adds to an object is location. And that's the difference between them. Okay, here we had another fellow, and I talked about him the other day. He's one of these bozos, clowns of the circus. And they have all these things which they learn by rote. They think the establishment cannot make any errors, partly because, all the mathematicians on planet Earth cannot be wrong, can they? I mean, if they tell you that, the flat Earth, should you believe it? And they say, well, after so many hundreds and thousands of years, these guys really know their stuff, and especially, the technology works. So everything that comes out of Harvard and Cambridge and all these other universities, hey, it's got to be the truth, fact, proof, verified, certified, the whole works. And so, yeah, when you get to people like that just believe in authority and they don't question anything, well, it's very hard to carry out a conversation. Okay, so this fellow, he criticized several of the things that I raised last week, and so let's go through a couple of them here. He says the blue star parts is his. Okay, physics adopted abstract concepts like fields and wave functions. Yeah, it was forced to do so because experiments produced results that were impossible to explain with a simple, classical, object-based mechanical model, which is known as the classical model, right? That in the old days they had these particles, these corpuscles, grains of sand, beads, whatever you want to call them, and that's what they moved around. And quantum mechanics came around and said, forget about all that. We cannot explain a single experiment with these little beads, so we're going to create the word particle, which is holdover from the classical period where they used to call it particle, but now the particle took on a different, meaning. They started talking about quantum particles and mathematical particles. What do you mean a mathematical particle? What is a quantum particle? Well, it's a particle that has different behaviors. Irrational behaviors. They don't behave like classical, like rational particles. They behave irrationally. Okay, this particle affects that one from a distance. We don't know how it does it, so it has a strange behavior, a weird behavior. It has a quantum behavior. And then this particle can also have the same location as this other particle, right? And one particle can have two locations. Now, how's that for irrationality? And they say, well, it's not irrational. It's known as a mathematical object. It's a quantum object. So that's what they did. They had to change the language because they could not explain not a single observation out there, or experiment for that matter, with classical particles. And so they kept insisting on the particle, but they just gave it new properties. They say, well, it's a particle, but it's a quantum particle, meaning an irrational particle does things that a particle wouldn't do, but we will keep the particle because we need the particle to explain everything. And instead of getting rid of the particle, instead of getting rid of the waves, the transverse waves, they kept insisting on them even to this day. And that's the whole problem. That's why he said they couldn't explain. Yeah, of course, because you're still using particles and waves. That's why you can't explain it. Okay, that's the problem. And so mathematical, which are misleadingly called physicists, right? They explain all experiments and all observations with particles. But you can't explain light with particles. You cannot explain gravity for sure. I mean, here's gravity. You let go of the pencil and it falls downwards, right? And the question is, if there's a force of attraction or even a force of pull, well, force of push you can explain, but gravity is known, and they concede it's a force of pull. How do you pull with particles? Is the Earth throwing particles at the pencil? Is that how you're going to explain attraction, by throwing particles at it? So no, you cannot explain a single phenomenon of nature with particles. We have to get rid of the particle hypothesis. We have to get rid of the wave hypothesis. Wave, because wave is not a thing. It's an abstract concept, mathematical concept. That's all it is. Anyways, that's the issue with particles, and the reason the mathematicians cannot explain a single phenomenon of nature is they keep insisting on particles and waves. We had to make a change, and change is a big one, the one we're proposing. We're saying that these waves that they've been talking about all these years is an actual physical rope. Okay? It's a rope, not a wave. Okay? And it's a torsion wave, 3D torsion wave, propagating along a rope, and not a 2D transverse wave going from A to B. Rope has the advantage that it's bidirectional. When it torques, both atoms at the ends receive the signal. And that's an advantage it has. Aside from the speed, torsion wave beats the crap out of a transverse wave. Transverse wave travels slower than longitudinal waves during earthquakes. In earthquakes, the longitudinal part of the wave travels faster along the Earth than the up and down, and you can see why. It travels 1.7 times faster than the transverse wave. So you can check that out. Anyways, so what does this bozo also insist on? He says the fields. Gaede dismisses fields as imaginary. No, not as imaginary. I dismiss them as concept. It's a concept. It's not that it's imaginary. It's that field is defined, as you see at the bottom, a value at each point in space. So there's no physical object called a field. But this is what this fellow believes. He says, however, fields are not just mathematical tools. They are physical entities with measurable properties. He's saying that these are physical things. That's what he's been taught. This is what he learned by rote. He just accepts this. Fields store energy. Well, how can they store energy if neither energy nor fields are physical objects? I mean, what are we talking about? Are you talking about storing like you store bullets in a gun? What are you storing here? Are you storing love inside intelligence? Is that what it is? An electric field between two capacitor plates stores energy. Yeah, I mean, what do you mean stores energy? Energy is a concept. You don't store concepts, okay? So, again, he's talking, he uses the word imagining. It really fits pretty much, what he's saying. Yeah, he's talking about imaginary stuff, really abstractions, mathematical abstractions, right? Concepts. Electromagnetic waves, what? Carry. They carry. I like the word carry. They carry momentum. That's what he says. This is what he's been taught. He just repeats the nonsense that he hears out there and just reproduces it. No, you can't carry momentum, whatever that means. You know, momentum's a verb. You don't carry verbs. I don't carry my run or my fly or my swim. Okay? Gravitational fields and time dilation. According to general relativity, gravity is a field. Yeah, field of what? Field of marijuana? What kind of field is it? Poppy field? Football field? A curvature of space-time. Again, space-time is 4 number lines, and what they do is they curve the number lines. So you try to figure that one out. One of its predictions is that time runs slower in a stronger gravitational field. Well, not true, because if you use a sand clock, in other words, an hourglass, and you take it closer to the center of the Earth, it runs faster than as you go further away from the Earth, because the gravitational field, as he calls it, is stronger closer to the Earth, and so the grains fall faster. Okay, so no, not true what he said there. If space-time and gravity, and by the way, an hourglass is a gravitational clock, so that's the best clock to check. If time runs slower or faster. If space-time and gravitational fields are not real, what object is causing the atomic clocks on satellites to tick at a different rate than identical clocks on Earth? Yeah, that's the question you got to answer. What object? You can't say space-time or a field, because those are concepts. So he doesn't understand that he's asking the question. He's asking the right question. But he's answering with concepts. He's saying it's space-time. It's a field. And he says if space-time and field are not objects, then what is causing it? They're concepts. So you got to tell me what physical object is causing the phenomena. For that, you need to define the word object. That's why we always come back to the word object. And people say, "Oh, Bill, you're doing semantics. We came here to do physics, and you're doing word salad." Yeah, you need to define what an object is for the purposes of physics, because they get away with this with murder here. He's saying field is an object, a thing, and he's saying space-time is a thing. And so we bend it, and now we can explain gravity. No, space-time is not a thing, so your whole theory goes down the drain, because you cannot say that space-time is a physical object that you can bend. Okay, and this is what field is, because what is field? A value at each point in space. So here I illustrated a field so he knows what a field is. Okay, here it is, folks. You see it here for the first time. There you have it. That's a field. Bunch of numbers, values in space. Okay, and they keep changing values. And here's a field, the Earth inside a field. Okay, that's a gravitational field. I don't know how you can tell, because they look like numbers to me, but they say, this is what the Earth is in. It's got this field around it, a field of numbers, a value at each point in space. And what these people are saying, hey, look at how we bend it. Here, we're going to bend the field. So they're bending the field now, okay? They're bending, these numbers. That's what the theory is. That's what Einstein said is the theory, that you bend a field, and a field is a bunch of numbers. Okay, so what sense does that make? It doesn't make sense to me. Maybe it makes sense to you. You're bending the field. Bunch of numbers, that's what you're bending. Okay, he continues, this fellow, he criticizes a lot of stuff, so I just chose a few. He says the double-slit experiment, the cornerstone experiment of quantum mechanics, is the most powerful refutation of Gaede's entire worldview. Okay, let's see. He says the very concept of a classical object with a definite position and momentum breaks down. It breaks down because you're using particles and you're using waves. That's why it breaks down. If you use something rational, maybe it wouldn't break down. And he never thought about that. He said, no, we tried, particles in different ways. We tried waves in different ways, and it always breaks down. Well, then you should have rejected the particles and the waves. That was the logical thing to do. You should have erased the board completely and begin brainstorming new objects, new mediators for light. That's what should have happened, right? It says, if you fire electrons one at a time, okay, he's talking about little balls. Okay, he calls electrons, right? And he thinks these little balls are, he can handle them one at a time. This is what he's been taught. And he says that a screen with two slits, they don't behave like tiny billiard boards. Of course they don't. I mean, we know that that's not the case. So you can't use balls to do the slit experiment. We're done, right? He said instead of forming two piles behind the slits, they create an interference pattern. The single electron seems to pass through both slits simultaneously and interfere with itself. So he's saying the electron is at two places at once. It's at one side of the slit and on the other side of the slit. That's what he's saying. And that's irrational, okay? And he says the single experiment demolishes the object-centric model. A classical object cannot be in two places at once. Exactly. So what you had to do is reject, throw away the particle notion, the particle hypothesis. You cannot simulate light with particles. Period. Done. We're done. This is the whole problem. They keep insisting on particles and particle. I'm going to do a particle. It doesn't work. I know. I'll bring in the quantum particle, the mathematical particle, and that's the one that can do it. How can it do it? Well, it's at two places at once. See how easy it was? So when you say, hey, that's magic, that's black magic, that's witchcraft, they say, no, it's quantum. We've proven it. You've proven it? How did you prove it? Well, we run the experiment and we find that, the fringes are on the wall. Yeah, but that doesn't mean that your explanation for that is correct. I mean, I can also explain the earth going around the sun with angels. Does that mean there are angels that are pushing the earth around the sun? I can explain it. I can't see the angels, but what else can it be if not angels? Come on. So this is what they're saying. What else can it be if not particles? We handled one particle at a time. Yeah, how do you know you handled one particle at a time if you can't see or touch it? That's the issue. But they keep insisting that, on the particle hypothesis. That's a whole problem. And on the wave hypothesis. Okay, those two have to be thrown in the trash can. Everything from Newton to the 19th century, where they replaced Newtonian particles with waves, and everything in the 19th century, where throughout that century they dealt with the transverse wave, all the way to the days of, what's his name? German guy. 19th century, 1900, what's his name? Max Planck. He came up with his black body experiment and analysis, and they gave him a Nobel for that. And what did he discover? He put the particle back in. And after that, we had duality. We had both particle and waves, and everybody just has the wave-particle duality, the wave packet. And now we explain it with a wave packet. How do we explain it? Very simple. When it does this, it's a wave. And when it does that, it's a particle. Okay, we fixed it. See how easy it is? And yeah, instead of rejecting wave packet, wave particle duality, all that nonsense that quantum created, no, they insisted on it. And people today are still trying to find meaning in so-called mathematical physics, right? They're trying to find meaning to this. Meaning, how can you find meaning unless you put it in classical terms? Otherwise, you're never going to find meaning because you're trying to rationalize it, and you're telling me a particle can be at two places at once. How are you going to rationalize that? The only way is, saying, well, the particle is at two places at once because it's a quantum particle. But that's not rationality. That's irrationality. And so when they say, well, we can't find any meaning and we don't understand a physical interpretation. Of course not, because you're cheating. You're saying the particle can be at two places at once. It's not that the particle breaks in half, okay? They're saying the particle is at two places at once. The elephant, Dumbo, he's at both slits. That's what they're saying. And so, yeah, that's irrational. And they don't like the word irrational. They say, no, we verified. What did you verify? You didn't verify a particle. You verified that there's fringes on the wall. Did you handle one electron at a time, one photon at a time? Well, there's no such monster. So you didn't handle, that's where the error is. You did not handle one electron. You did not handle one photon at a time. You thought you did because you're using the irrational planetary model of the atom that Bohr created, Bohr and Rutherford. That's why you're using the electron bead that circles around. Now you're going to send it through the slits. That's where the whole thing collapses. Okay, so here's Another issue the bozo brings up, he says, wave-particle duality. Light and matter exhibit both wave-like and particle-like properties. This duality is a core feature of reality. Is it? Who determined, how did you determine that we have wave and particle? And so, yeah, they come up with this nonsense. The mathematicians came up with it because they had no explanation. And again, they say, look, we don't understand it. Of course you don't understand it because you're cheating. You're putting magic, you're putting witchcraft in there, and you're trying to make sense of it. No way. Quantum tunneling, a particle can tunnel through a potential barrier that classically it shouldn't have enough energy to overcome. Well, nobody has energy because energy is not a physical object. Energy is a number, and nobody has numbers. Okay, so that's the first one. You can't use the word energy in science, not in physics, not as a physical object. Energy is a concept. And it's when they treat it as a physical object, like here, he says, oh, we don't have enough energy, And people say, well, isn't the gas in my tank, isn't that energy? No, it's called gas, not called energy. Okay, energy is a value, okay, of your gas, some kind of value there. It's not, you can't say that gas is energy, okay? And again, it's because people introduced language of ordinary speech into science when they say those things and they think they can get away with it or are not aware that they're doing so, right? And so it says, this is a real phenomenon that is essential for nuclear fusion in the sun and is used in technologies like tunneling, electron microscopes, etc., etc. How does a physical object, right, here comes a good question, pass through a solid barrier it does not have the energy to break? This is explainable via the probabilistic nature of the wave function. Yeah, it's not an explanation if you're going to use probability. That's not an explanation. As soon as you get into, wave functions and probabilities and that kind of thing, you're not giving an explanation. You're giving a description, but you're calling it an explanation because you think you've explained something. Now, an explanation and a description are not synonyms, and an explanation is not a bunch of description. Okay, you need to, the difference is the causes. You need to find what the cause is, and a description doesn't tell you the cause. Okay, and maybe tell you the mechanism. You observe something, say, okay, the machine did this, this, and that. That's a description, and it gives you an idea how the machine works, a how. Not why it did something, but how it works. But it doesn't tell you the causes, never. Okay, and so here we have. Talks about space-time, this bozo. He says, gravitational waves. In 2015, the LIGO experiment directly detected gravitational waves. What are those? Ripples in the fabric of space-time itself. What was space-time? A bunch of number lines, 4 number lines. And he's saying that the number lines are waving. Man, that's got to be something. When you have a number line that waves, it's because you had too many beers. That's what the problem is. Caused by the collision of 2 black holes over 1 billion years ago. Well, yeah, 2 black holes cannot collide, right? Why? Because a black hole is a zero-dimensional nothing. That's what it is. A singularity, right? It's a concept, which is the center of the black hole that ends where? At the event horizon, another concept. So what we have is a center of an event horizon, which is the region of influence of the center. And what's in that center? Well, there's 2 versions. One is that it's zero-dimensional and infinite energy, right? Infinite mass. And the other one is that it's a hole in space, or space-time, I guess, and you never reach there. Everything falls towards the singularity, but never reaches there. And that's where the laws of physics break down. And that's the language that they created, that they spread to people out there. And, all these people believe this language. They just repeat it. Okay, and he says, if space-time is nothing, what was it that rippled and traveled for billions of years across the vacuum of space to physically stretch our detectors? Yeah, that's the question you got to answer. That's what you have to answer. And these people don't answer the question that they're asking. The what's. What is space-time? And so he's saying, the way he phrases it, he's saying what else could it be if not a physical object? Because if they detected waves, the waves were along what? Well, it's along space-time. It's got to be along, the space-time fabric, right? That's what waved And so they're treating space-time as a physical object. He says, well, what else could it be if not an object? Because otherwise, what's waving? But that's a question you have to answer. And you can't say space-time because space-time is not a thing that waves. It's not an ocean. And space-time is not a bunch of air or a bunch of water or whatever, gas. No, space-time is a concept, and you don't wave concepts, hopefully. Okay? It's a description. Okay? It's an irrational, it becomes irrational when you turn the space-time into a physical object. That's where Einstein's theory falls completely into pieces. And again, people don't understand exactly, what Einstein did. They say, well, why is Einstein so famous with his field equation? What does the field equation do? And it's very simple, just the notion, just you don't have to know any math for this, okay? Just think of, you take Mercury, which is the planet they applied it to for the first time. You take Mercury, and it weighs so many tons, right? All that matter in there in that ball, okay? And you squeeze all that matter into a point, okay? So now you have all the mass of Mercury into a single point. Okay, we all understand that? It's a conceptual issue, right, so far, right? And now you're going to move that point, the point. They're not going to move the planet. That's the first error. You don't move the elephant. Now you get rid of the elephant because you squash the elephant to a point. Now you're going to move the point. In science, we have to put the elephant back if you're going to move something. Because a point is not something. It's a concept, the center of mass. Okay, that's the first problem. But let's forget about that. Okay, so now we have the little point, the center of mass that's moving around the sun. And what Einstein did with his famous field equation, he says, look, field, what is it? A bunch of numbers, right? Keep that in mind, right? So as soon as this point reaches a different location, it presses down on the field. It's in a different location, so now it has a different value of the field at that location where the point is at. Okay? So the point moves, like if you're walking on a trampoline, right? You press down, right? And so at that point, you kind of have a different value for your weight, for whatever you want to mass, whatever you want to measure at that point. It's got a different value because you press down on a trampoline. But what happens? The next step that you do has been affected by the fact that you press down on the trampoline. So you press down on the trampoline, it's got to affect your next step. And that's essentially what the equation does. It says you got this point mass, it presses down over here, but now that you've modified the surface of space-time, it changes your next location. And again, you press down, changes your location. You press down, it changes your distance, etc. And so what Einstein did, he calculated with his equation the orbit of Mercury and was able to show that if you apply the equation, this is just math, right? You could describe the whole, orbit of Mercury, because it shifts its perihelion with time. Over time, it creates a Rosetta type pattern. And the way he explained it is, again, pressing down on space-time. The concept, the mathematical concept, I have no problem with. They can keep it. It has no bearing on physics. We want to know the physical explanation. And what Einstein is saying, you press down on a trampoline, the trampoline affects your next step. That's what he said. What's a trampoline? Space-time. What is space-time? 4 number lines. So that's the Mercury's perihelion shift in 2 seconds, in 1 minute, whatever. Okay, so this all continues. He said, bgaede's model is not a scientific theory. Oh, okay. It is a philosophical stance rooted in a common sense, okay? Mechanical intuition that was rendered obsolete by the physics of the early 20th century. So he's saying when they came up with quantum mechanics, they threw all the philosophical stuff, whatever they call philosophy, right, in the trash can. And they said, we're going to proceed with quantum mechanics. Okay. Science progresses by creating models that explain observations. Absolutely not. Not what they call science, because in their version of science, as I showed a couple times already, explanations are no longer a part of science. They say science describes, science does not explain. So every time you see the word explanation in a definition of science, it is absolutely wrong. Okay? There are no explanations in science. There are only descriptions, mathematical descriptions, because the mathematicians have equated science with mathematical physics, with math. Modern physics is abstract and mathematical precisely because experiments have proven, they always prove with experiments, right, that reality is abstract and non-intuitive at the fundamental level. So what he's saying is, he's going to rely on experiments for stuff that he can't see or touch, and he calls that a proof because he sees the results of that invisible, tangible matter. Okay, and again, the angels move the earth around the sun. I've proven angels. Why? Because, hey, the earth does move around the sun in orbits. And what else could it be if not an angel pushing the earth? Well, one pushes, the other one pulls, okay, just in case I cover all the bases, right? To accept bgaede's model is to reject the mountains of experimental evidence. Again, experimental evidence, what is that for? To fool the jury. To fool the jurors and say, I want you to believe like I do. I'm the prosecutor of the case. I want you to believe like I do, and here's the experiment. I hope I will convince you with this evidence. And that's what all that experimental evidence is about, to persuade people. It's not to explain objectively a cause or mechanism. That have been accumulated and verified globally for over a century. In other words, he's saying all these guys raised their hands and they voted for it, and that's democracy, and so we will rule you, Bill. Your stuff is not scientific. Physics moved beyond a purely object-based model because the universe, through experimentation, showed us that it had to. Okay? And here, let me bring some authority to bear on what he just said. Here's a bozo, another bozo, but this is a certified bozo, okay? His name is Leo Susskind, and he's he's Professor Block, called Professor Blockhead of Stanford University. So you better pay attention to him. What he says is absolutely true. Okay, he says modern science is difficult and often counterintuitive. Where intuition and common sense failed, they had to create new forms of intuition, mainly through the use of what? Abstract mathematics. So all these people are doing math. They don't know anything about physics, but they call it physics. When common sense fails, uncommon sense must be created. Human cognition does not operate according to principles of common sense. So I guess they're telling you that, what they do is uncommonsensical. The least common of all senses is common sense. And here, good old Leo proved it, right? Then he came up with this nonsense that, they had to get rid of rationality and create uncommon sense, which he calls, the math that he does. So that's why all these people believe in this nonsense. They believe it on the basis of authority, and they were duped by people like Susskind and Ed Witten, who go out there and throw math at them and say, oh, we proved this mathematically, here's the equation. And since nobody understands all that garbage that they scribble on the board, they said, well, I guess they proved it. Look, there are the symbols, the hieroglyphics. And so it must be true, and so they proved it. And since many mathematicians proved it, hey, it's a done deal. And we have to believe that space-time warps and that particles can be at two places at once and all that good stuff. And that's what these people believe. This is how they explain the universe, or don't. Okay, moving on here. See if we can catch up on our time. Fellow asked why light bends, essentially. He asked me this question about 2 weeks ago. I gave him a rain check, and I got to answer his questions, okay? And I thought it was a good question. He says, why a beam of light enters a medium and refracts? What determines the angle in which the light bends? Like it goes into a prism, and suddenly you see that sharp bending, and then bends again when, goes out the other surface, right? And he says, what determines the specific path of where the light signals end up. And I think a lot of you have seen, the prisms and light going through there. You can look it up on the internet. You'll find tons of pictures of that and videos, etc. Right? If the light signals just propagate through random paths and doesn't pick a direction, then the whole medium would light up. In other words, if you take a light bulb, light goes in every direction. And so he's saying, why does that light go like in a directed path? Why doesn't it refract and disperse, sideways and go all over the prism, for example, right? And so that's the question we're going to try to answer today, okay? However, in real life, the light beam always travels one path after entering the medium, okay? So he wants to know why that pencil sharp, pencil beam, ray, I guess you could call it, why it goes completely straight. That's the question. And also related to that is, does light bend? Does light curve? Primarily curve, Bend like sharply? Yeah, we can say it bends, whatever that happened there, right? We got to explain that. But does it curve like, in a nuanced way, little by little? Is that what light does? It curves? And then the other issue we need to answer, which is the main subject today, does light go through walls? Can you see through walls? Like if I put a flashlight on the other side of your wall, can you see? I mean, I'm talking about a real wall, like made out of bricks, right? Can you see through the bricks, the flashlight on the other side, or a candle, or whatever you want to put there? That's the question we have to try to answer today, okay? See if we can. Okay, and essentially he's talking about this prism, right? You've seen that. You have this white light coming in from the left, goes through the prism, and it kind of breaks up in all these colors, typically 7, right? And then it comes out of the other side also as a bunch of colors. Okay, and the question of what happened there, how did we break up light in all these colors, and why is it bending? Why does it bend? Okay, that's part of the question. And again, I think right there we more or less get the idea that light does go through solid matter. I mean, a prism is solid, but it's translucent, so you can see more or less through a prism, not completely. It's not a perfect glass, right? But you can see on the other side, and light does seem to be able to go through solid things. Okay, that's the issue. Okay, but what's one of the problems with this? One of the problems is the speed and the outgoing speed. The light is coming in at 300,000 kilometers per second. We're just going to assume that this is done in the vacuum, okay? Or air is very close to vacuum as far as what is known as a refractive index. But let's just assume it's a vacuum. You're in the vacuum. You're out there in space. You're going to shine the light. Okay, it's going to go in there 300,000 kilometers per second, right? And it's going to hit this wall, slanted wall of the prism, right? And here it is. Here's a picture of it so that you can see it. The question is, it comes in as white light at 300,000 kilometers per second. And then the question is, they say, well, when it hits the prism, its light slows down. Okay, light slows down. That's their explanation. They say light travels slower. And as you can see, it breaks into different colors because they have different wavelengths. Okay, but the bottom line is they say light slows down because it hit a brick wall. Essentially, that's what it is. And what's happening, according to them, the mathematicians, right, is that the atoms inside the prism are absorbing the light and re-emitting the light. Okay, and they do so probably from atom to atom or from atom to the space there on the right-hand side, right? Whatever the case, they're saying that atoms are absorbing and then re-emitting the light that they receive, the white light. And so they have these different wavelengths for each one, and that forces the beam to bend. Then it bends again once it reaches the other edge. The problem here is that now light has to go fast again because it goes back into outer space, right? And so the question is it traveling fast or slow when it comes out on the other side, on the right side of that prism? And so that's one of the questions we need to answer as well, right? The speed of light. What makes the light go fast again? I mean, if it slows down inside the prism, how does it pick up speed afterwards? Okay, that's the question, right? Okay, and so here we have another explanation from the R2D2 or the AI, right? The bots. And it said when light passes from a denser medium to a less dense medium, it speeds up. Why? Because it encounters fewer interactions with the medium's particles. In other words, they're saying that inside the prism, the atoms it's a denser material. It's solid, it's denser, and so we can imagine, you're going with your car and suddenly you hit a brick wall, right? Or you travel through some kind of, haystack maybe, right? And you go through the haystack. While you're going through the haystack, you're going to go slower, right? But then when you come out the other side, well, your speed should continue normally, right? That's essentially what they're saying here. It says, well, light travels at a constant speed in a vacuum of 300,000 kilometers per second, right? It slows down when passing through a medium due to interactions with the medium's atoms. In other words, there you see a piece of glass maybe, prism, you see it sideways, no problem. It goes into the prism, goes slower, right? Once it exits the denser medium and enters a less dense medium, these interactions decrease and the light speed increases. But they haven't explained why it increases. I mean, and here, let me show you what I'm talking about. Now, I'm going to illustrate it for you so that you understand the question. The question is the question. What is the question? Here it is. Here's a car. Okay, I'm going to run this. You're going to see a car going through water. You're going to see, in fact, two cars. The first car is going to go in there, go slower, and then continue at the speed it was going through, right? It was coming through. It was coming at 60 miles per hour, goes maybe to 40 miles per hour, then continues at 60 miles per hour. The second, I think it's a truck, goes in there, and it's stopped altogether at some point. And then it has to restart and move on. And so the question is, how do you explain that for light, assuming it comes to a complete stop? Can light come to a complete stop and then start again all of a sudden at the same speed, 300,000 kilometers per second in a vacuum? It'll go from 0 to 300,000? How? How did it do that? That's kind of a magic trick. So here it is. Watch this. Here's the two cars. Now the next truck is going to get stuck. But this one stops. And then it cranks again. And only then does it leave, okay? So what happens if we replace the car and the truck with light? I mean, light slows down, goes through a medium, then continues at its regular speed because it doesn't encounter as many atoms. Is that the reason? Or is it because, it cranked the motor up again? And how about if light comes in there and stops altogether? Now you have to restart the motor, right? And just in case, I want to make sure people understand that the mathematicians have proven evidence, verified, completely proven. They have the evidence that they stopped light altogether. Zero motion of light. And the first one was done, I think, 1999. The second one was now, they tried several times, but they tried again in 2015 or 16. Here it is. Okay. And so quantum computing scientists stop light in a cloud of atoms. And they say a cloud of atoms seen here as the red glow in the middle of the images was used to make the stationary light. And in 1999, a team at Harvard University successfully slowed a beam of light to a crawl. Then in 2001, they achieved the seemingly impossible, completely stopping a light pulse. This was done by manipulating light within an extremely cold cloud of atoms. Okay, so they froze the atoms, and by doing so, they froze light. Then they were able to restart the light, essentially releasing the stored information back into a light pulse, which then traveled on as if nothing had happened. Okay, so just like the truck, it stopped altogether, and then the truck continued moving. Okay, so here's light coming into a prism, right? Here's a prism. Okay, here comes light. Okay, hits it. It goes slowly. And if you want, stop it altogether. But then the question is, when it comes out, does it pick up speed again? And if so, what compelled it to pick up speed? Why does it travel again at 300,000 kilometers per second? I mean, we can understand a car, okay, more or less. Car travels at 60 miles per hour, hits the water, right? But its wheels, everything is still rolling at 60 miles per hour, right? The only problem is being stopped by the water. But now you remove the water. In other words, it goes into the medium of air again, and it goes back to 60 miles per hour, because that's the speed at which the wheels were traveling or rotating or whatever, right? We can more or less understand it there. But how about the truck? The truck stops altogether. How do you restart it? And these people say they stop light. And then the next second, they just melted these atoms, they got them moving again, and light again traveled at 300,000 kilometers per second. By what mechanism? How did it go from 0 to 300,000? That's what I want to know. Okay. And this has been confirmed here. Here we have Derek Muller. He's a guy who peddles the party line, and he's going to tell you first that how these waves are created, the waves that travel, because I guess it's done with waves, right? And he's going to tell it to you. There it is. Listen to him.
Electromagnetic waves are made by accelerating charges, like by wiggling them up and down. Then the changing electric and magnetic fields they create team up as light and head off on their own.
Okay, so he's saying that there's something called a charge that moves up and down, and that's what the wave is, the wave of light, right? So he sets that up, and then he goes in there and he's going to explain that if the wavelength shortens, right? Listen carefully here. If the wavelength shortens, right, but you keep the frequency the same, then you have slower light, okay? So listen to him again. Here it goes. Give me a second. Here it goes.
Higher frequency light, like blue light, will cause the charges to wiggle with greater amplitude. And because of this, the charges produce higher amplitude electromagnetic radiation, which shortens the wavelength proportionally more, making higher frequency light travel slower and bend more than lower frequency light.
So let's see if I understand him correctly. He's saying you have little c, right? Little c is equal to 300,000 kilometers per second. That's the speed of light in a vacuum, right? More or less in air also, okay? Okay, so you have that speed of light, right? And the question here you have the equation. This is what he's saying. He's saying that if little c is equal to 300,000 kilometers per second, and you have frequency and wavelength, a little f and the f there and the lambda there, okay? If you lower the lambda, if you shrink the wavelength, right, and keep the frequency constant or raise it a little bit, I guess, then little c is going to travel at a different speed. Instead of going at 300,000 kilometers per second, it's going to go at 100, for example, in this case, right? And so the question is this possible? Can you slow light down? And if you can, then how do you speed it back up again? I mean, how do you raise the wavelength again? Okay, by what mechanism? And they never explain that. They just say, it is so. It has less things to bounce against, less atoms in the less dense medium. And you can't get anything less dense than, I guess, space, right? So that's where 300,000 kilometers per second. But see, if this is true, if you can fool around with a wavelength, right, and you can fool around with a frequency, why not raise both the frequency and the wavelength and travel faster than light? See how simple it was? You want to travel faster than light? Instantaneously? Hey, there you have it. Just raise the frequency to infinity and the wavelength to infinity. Why can't we do that? What physical impediment do we have? What stops us from doing something like that? And that's the question, you got to answer. These people avoid these important questions. Okay, so here we have, I'm going to try to explain, the couple of questions that we've got here. The first one is, why does light travel straight? Why is it directed? That's one issue. The other one is going through walls. Why does light go through walls? Okay. And another one is, again, this bending thingy and the speed of light. Those are important questions related to light. And we're going to try to answer all these questions now. Okay, so here we have a light bulb, okay? And you can see that just by looking at the picture, you can see that light is going in every direction. It's going radially. Okay? Light bulb doesn't direct the light in one direction. It goes in every direction simultaneously. Okay? And that's what I'm showing there. Now, what is our version of the atom? Okay, here's one atom, only just one atom, okay? And you can see our atom is made out of this electron shell, electron membrane, which is weaved by all these threads, the red one there, going around, and that encapsulates the proton star. So the atom was not what they told us all these 100 years now. Here you have a comparison between them. You have the, let me put it in motion here. Okay, so here you see our atom is just pumping back and forth. That's the quantum jump. And by doing so, it torques every rope that converges upon it. And all these ropes come from every single atom in existence in the universe. Okay, so let's get at least the notion of what we're proposing right. Okay, you don't have to agree. We're making an assumption here that an atom looks like that, like a ball of yarn encapsulating a star. One thread goes to the center of this ball, and the ball is made out of the other threads that go around. And those two threads, they come from the ropes, the electromagnetic rope, which is a pair of twined threads. One thread goes straight, and the other one curves around. That's it. That's our model. Okay, you don't have to believe in it. That's the one we're going to use to explain. Okay. On the other hand, you have the ridiculous planetary model that you see on the side there, on the right-hand side, which is the electron bead. That's what they think the electron is. And this electron bead jumps back and forth between energy levels. By doing so, it absorbs and releases energy, whatever energy is, right? Not a physical object, it's just a number, just a value that they calculated. And yeah, and that's what they're saying. And all these waves that you see there, the transverse wave, they come out. That's the energy that's flowing outwards when the atom falls, or they come in when the atom absorbs energy. That's it. Okay, that's the quantum jump version of quantum mechanics. Okay, and so the question is whether this in any way represents, what we have out there, what Mother Nature does. And here, we're going to put the bulb that we just showed, we're going to put it with a single atom, just one atom. Obviously, a bulb has gazillions of atoms. We're just going to put one just to illustrate the fact that light is coming out of there radially. Okay, so here it is. Okay, that's what we're saying. We're saying here we have the bulb, and we're assuming there's a single atom. We're just looking at one atom in the center, and that one has all the ropes converging upon it. It's vibrating, and all the ropes are being torqued. That's why light travels radially. That's the direction of light when it's not contained in any way. Okay, so what we're going to do now, we're going to contain it just to show how we direct light. And here we have the same bulb, okay? And you can see we've chopped off, somehow blocked the light bulb from every angle except, given direction. The front side, it can go straight ahead. But you can see that a lot of the ropes are going sideways, and they crash against whatever black stuff that we use to contain the light. So they hit there and they die there. In other words, they don't go through on the other side of that black container. Okay, we'll call it a container. Okay, and only the ones that are going forward are the ones that are going to make it like a sharp pencil, a ray, a beam. Okay, and so just want you to understand that concept that we're blocking the light from all sides. We're directing the light in one direction at this point. Okay. Okay, so let's see where we go here. We need to show this before we move on, and that is that we're going to explain the spectrum of light. We're not going to explain it like they do in quantum mechanics. We're not going to use the wave, the transverse wave, the standing wave. No, we're going to use ropes. Okay, so we're going to replace the entire spectrum with ropes. Okay, so you can see there, if you want to see the violet has shorter lengths, right? Shorter lengths than the red. Red has longer lengths. Okay, so that's what they've been looking at all these years. According to us, we're saying that there's no such thing as a wave. You need to identify the object, and the object is a rope, and all we're talking about the different lengths of the lengths of a rope. That's it. And so when you have a torsion of these ropes, you have links which are shorter, and you have more links per unit length, and vice versa. When you have red ones, for example, there, the links are longer, and you have fewer links, meaning the frequency is lower. Okay, that's what essentially we're simply replacing the wave with a rope. Everything else remains the same. There's no difference otherwise. Okay. Okay, so here we have a prism. Okay. We're going to look at that first. Here we have a prism, and we see how light is broken down. It's broken up into pieces, okay? But we're going to replace this with what? Well, with what we just showed, with the links of ropes. We're going to replace them with ropes. So what we have is ropes torquing inside the prism, and when they come out, we still have ropes, okay? And one of the questions we need to ask or answer, I guess, is why do we have those different color ropes, and why are they coming out also with different colors? And has the speed changed, okay? I think we're already more or less answering that light does go through walls, okay? Because you have a wall there of a prism. It is a wall, it's a solid wall, right? And it's going right through there, okay? So keep that in mind. Okay, so one thing that you have to keep in mind is that all this can fool you, because you're seeing the light, from a distance. You're from a bird's eye perspective, right? So you're seeing the light go in. You're going through the prism. You see all of this, right? And you see the light coming out. Okay, you see all that. But what are you seeing? Are you seeing what Mother Nature does? Are we confusing the observer with what's actually happening with light going through the prism? Okay, we need to distinguish those two. And so this is the observer's version here, okay? The observer is seeing light that is being reflected and refracted towards his or her eyes, okay? So light is being pumped by those atoms inside the prism, and it's redirected. Some of it is going straight and going to the other side, and some of it is being reflected or refracted, I'd say refracted in this case, right, towards your eyes. And also from the beam that comes out. I mean, you're not staring directly from the front of where the beam is coming into your eyes. No, the beam is going sideways, and it's stimulating air atoms, air molecules, right? And those are the ones that are arriving at your eyes. So you're looking at this whole thing from, you have a side view. Okay, you have this side view of this whole phenomenon. Keep that in mind, okay? Because it gets complicated after a while, when you're saying, what am I staring at? Well, you're seeing light coming to your eyes. Say, okay, the light went that way. Yeah, the light may have gone that way, but what you get is the observer's version, which is light being refracted towards your eyes from the atoms that are being stimulated as the beam goes horizontal to your field of view, okay? Okay, so here we rub it in by showing what happens with a lens. Lens, you can think of it as two prisms, one against the other. Okay, so here you have a lens, and you can see the pattern that develops when you shine a white light from the top, right? You have this concave version, and it goes downwards. And the white light that goes from the bottom, because it has this convex, it's concave, but in the opposite direction, it forms this red point farther away, and the blue is closer by. And that's going to be very important because remember, blue has shorter wavelength, right? Shorter links, and red has longer ones. And you can see there now part of the answer of why we see this, okay? Because what you're seeing there is exactly that the blue will have shorter wavelength and the red will have longer wavelength, okay? So that's one issue. The other thing you should keep in mind that if little c is equal to frequency times wavelength, if the wavelength changes, like it's longer or shorter, frequency will change in the opposite direction. They're inversely proportional. Okay, so here's a laser pointer. Yes, all of you have seen one, right? There's a laser pointer. And we're going to put some atoms in there, but we're going to put our atom. We're going to put the rope atom, rope model of the atom. Okay, we're going to put several of them in there. Okay, so here you see them pumping. Okay, but what happens with the atoms that are inside the tunnel, we'll call it, the body of the laser pointer? Well, whatever light comes out of there from the sides, right, just gets chopped off by the enclosure. The only ones that will be allowed to go, right, to move, are those that go towards the right, in this case, in a straight line almost. So you're redirecting light in a given direction. You're sending light in a given direction, whatever sending means here, okay? So I just want you to see how light is not going, the light from the sides, you're not going to see it. Even though light does go to the sides and even goes past the enclosure, we're going to find out why you can't see the light that doesn't come through walls in a minute. But right now we're allowing only the light that goes towards the right through a little, pencil beam, ray, whatever you want to call it, typical of a laser pointer. Okay, and so here's light coming out of there. Okay, we're going to annihilate all the ropes that are coming towards the sides. There are ropes going through there because every atom in the universe is connected to all others, according to our proposal, our hypothesis, right? And so all atoms are interconnected. That means there are ropes extending from those atoms to your eye, even though they go right through the enclosure. But the light that is being stimulated, right, by these atoms, that one can only go through the opening that you have there. And that's how we direct light in a given, send it in a given direction, so to speak. Okay, so I hope you understand that part. Okay, but I just wanted to set that in there. In other words, if you have a laser pointer, right, and I'm going to use the light, not the because it's a very small pinpoint red light. I think it's 620 nanometers. Anyways, we have light, okay, and you can see the light, but you're saying, why doesn't light come from the sides? And yeah, whatever's creating light in there is going through the sides as well, but it's being blocked by the enclosure. And we take that for granted. We say, well, yeah, it stopped light. That means light went down to zero. Light stopped at the atom on the wall and doesn't move anymore. It just ended there and that's it. And no, according to the rope model, the ropes extend outside here. They extend right out of there, right? And go to other atoms, including right now to atoms in my eye. Okay? And so I can't see the light, and the question is why? Why doesn't the light, the visible light, go through the walls, right? It only goes in that direction. Yeah, okay? So the only light I can get to see is the one that comes out of the front end, because that's not blocked. What's blocked is from the side. So we're directing light, in other words, right? Okay, now the question is, light can go through walls. Can objects go through walls? And people say, well, no, objects cannot go through walls. And that's a lie. That's a total lie. And I'll prove it to you today. You heard about Superman, right? Well, there was a show, Superman, in the 60s, 50s and 60s, with George Reeves, who I guess committed suicide. He was on the news lately. Anyways, and he showed that, he could see through walls, which was a weird way of doing light, because light was not coming from whatever he was seeing. Light was coming out of his eyes. It was X-ray vision. So the light was going out of his eyes through the walls to see, Lois Lane taking a bath or whatever, that kind of thing. On the other hand, if he wanted to go through walls, yeah, he's the man of steel. He'd just break through there, right? That's the notion we have. Today I'm going to show him in exactly reverse. He's trying to use his X-ray vision. He can't see through the wall because it's a guy who built this prison, right? He's in there, and Superman's got to get him out, take him to court. If 7 years are up, well, the statute of limitations runs out on him. So he wants to get inside that room and get this guy out, right? He wants to talk to this guy or whatever. And the point is, he wants to go in, but he's not going to break in, like break the whole place up, because he apparently can't break it. But he does something else. He blends, he flows through the wall, okay? But at the same time, he can't see through that same wall. And here it is. So it's the other way around. His X-ray vision is no good here. And here's the visual part. Okay, listen to this. And I like it because one of the mugs there, he says, I think you need glasses. You need glasses, or maybe you're getting too old. Listen to him.
You need glasses, Superman. Oh, you're slipping, old boy.
So Superman needs glasses. Forget about X-ray vision. But this is how he goes through a wall. He's a body now, okay? We're not talking about vision here. We're talking about the body, okay? And so let's see if this is true, okay?
Of him. He's coming after you, Paul. He melted in the wall as if it soaked him up. If he shows up in there, tell him we've got Lois Lane and Jimmy Olsen.
Hey, wouldn't it be funny if he got stuck in the wall and never could get out?
See how easy it is? You just put yourself close to the wall and just try to seep through it, That's the way it's done. Anyways, yeah, if you want to try it one day and tell me how you did, if it was successful. Anyways, waves, can they go through walls? Okay, and here we have a candle, right, in the dark somewhere, and the light's going to go through that wall and reach the guy's eyes. Is that possible? Does light go through walls, or does it stop at the wall? Well, what's happening there, right? And here's proof, evidence, okay, one piece of proof evidence. People like proofs. It's known as the Wallabat, and it's used by electricians and so on, so that they can locate wires on the other side of a wall. And it's done through light, right? Different versions of light. It's an X-ray thing. It can go right through the wall and detect if there's a wire or a cable or a pipe, so that when they drill, they don't break it. Okay, so yeah, at least X-ray goes through walls, and what is X-ray? It's light. It's just a different form of light. It's an invisible light for us, right? For our regular eyes. So there's the first proof that, yeah, light does go through whatever light is, right? I mean, it goes through the walls. Okay, it can go through walls. And here's the rope going through walls. Again, you can see it there with the little candle, and you have an atom that's pumping right at the tip of the candle, and it's pumping right through the wall. But why can't you see it? Why can't that fellow there, why can't he see that light? Why can't he see the candle? Well, I've had a talk with my son Adrian. We have two different theories for this. So, you might come up with even a third one or a fourth. And that is, in my version, the atoms from the wall are pumping also towards his eyes. And there's a lot more of them. And closer to him, that's one issue. But all of them are pumping at a slower rate, or at a different rate than the candle, right? So you have, a lower frequency and higher wave length. That's why the guy can see the wall, but he cannot see the candle behind it. Now, that atom that's pumping there, it's connected directly to his eye, right through the wall. The rope goes right through the wall, but it goes through the atoms that are in the wall. It goes along. It's superimposed on all the other atoms that are in the wall, the ropes that are coming from the wall. So it's like you have a high frequency within the low frequencies, but the low frequencies by far, are eclipsing, you could say, the what's coming from the candle. My son has a different version. He says, according to him, he thinks what's happening here is that the atoms are somehow squeezing, the light out of the candle. In other words, those atoms are connected also to the atoms on the wall, and they're slowing down the frequency of the light coming from the candle, from the fire there. And so those are two versions. We're still fighting. And of course I'm always right, so he's got to be wrong. Okay, so we're going to figure it out. Anyways, my version is you have, once again, right? We have every atom of the candle is connected to every atom in my eye. Okay, every atom of the fire is connected to every atom of my eye, right through the wall. But why don't I see the candle? Well, because the atoms in the wall are, in other words, the ropes are going right through the other atoms that are connected to my eye. They are filled with ropes as well, and so we have the light from the candle going through all this coaxial of ropes that are also going through to my eyes, and so they're being suppressed. You could say they're they're being eclipsed, and so I'm not receiving the light from the candle, even though the atom there is connected to the atom in my eye. So yeah, even under the rope model or under a quantum model, light does go through walls. The question is, why can't we see through the walls, right? Like good old Superman to try to see through the wall. Okay, one thing that might help us explain it are the rainbows. They will probably help us explain at least the prism. Okay, here it goes. We have here these rainbows, and you always wonder why they're circular. Well, they're circular because they really go underneath the ground as well. If you had God's eyes and you could see through the earth, well, you would see the rainbow go all around. Okay, so it's a circular type of pattern, and we only see half of a circle only because the ground is in the way. But what I want to show you here is that what is known as Alexander's band, and that's between the two rainbows. The one on top being, you can see the farther out is a little lighter. It's not, you can't see it as well, It's not as, it's fainter. It's not as visible as the other one. And what's happening here is you have this region between the two rainbows. The rainbow that's brighter and the rainbow that is darker, you can see there's a region. And here, let me show you what I'm talking about in a better picture. You can see between the rainbows, right? That region, and that region's called Alexander's band. Okay, and the question is, why does that form? What's happening there? Why are we seeing nothing there? Why aren't we seeing a rainbow there? And why are we seeing another rainbow farther out? So we need to kind of answer that question. What is happening there? Okay, so here's a first approximation to an answer to that question, and that is that it happens also with the slit experiment. Okay, when you do the slit experiment, we don't see it, right? But the fringes, each one of those fringes has a rainbow in it, and as you can see, the rainbow has, on one side they go in one direction, and then on the other side they go in the other direction. You saw how the lens showed that from the bottom shows differently than from the top, because the blue one is closer to, it has a shorter wavelength, and this is the same thing that you're seeing there. It's the angle, right? And by changing the angle, what you're seeing is, the rainbow changes direction. If it went from blue to red, now it goes from red to blue, right? And so it's important to note that during the slit experiment, you do get the rainbow, but you got to do it really, really good in order to get that rainbow. Not everybody can do that. You got to have the right equipment, etc. Okay, so here you see it again. Okay, why the rainbow? Why you see the blue on the inside and the red on the outside, and that's because the blue is the shorter wavelength, length in our case, right? What you see, the distance between the eye of the observer and the blue and the red, well, there's a difference in length. Okay, and what we're talking about, the length of the rope. So that essentially gives you the idea of why the rainbow and why also the prism, right? Because that is the explanation for both. Things that you must keep in mind, things that quantum mechanics cannot answer with its wave, right? And with its particle, and it's the speed of light, why it's a constant. And we can with a rope. There we see why, and I always show this. The links, if you have many links, if you tighten this up, you get many links. You have more links, and length is shorter. But as the links get longer for the same amount of rope, you get fewer links. And that's what the equation C equals frequency times wavelength represents. You can't do that with a wave or with a particle. You cannot explain that at all. In other words, you cannot explain the constancy of the speed of light. And that's why they have to shorten, they say, well, we shortened the wavelength and now light travels slower. Yeah, and they even brought it to a full stop. Yeah, show me that. Okay, that's their interpretation. It doesn't mean that they really slowed light down from 300,000 kilometers per second to 100,000 kilometers per second. But that's the idea these people have, because they're talking about particles, photons, right, hitting atoms, being absorbed and re-emitted. And they say, well, if you have a lot of atoms and it's doing that a lot of times, and that slows light down. But then the question again is, when it goes back to the normal medium, why does light pick up speed again and go back to 300,000 kilometers per second? So that's one thing that the rope model answers, which the wave or particle hypothesis cannot answer. Here's another one. It's called ray reversibility, and you never hear mathematicians talk about it at all. But ray reversibility also debunks. I hate to use the word debunk because that's an opinion. It just shows that you cannot really explain a phenomenon such as ray reversibility with either the wave or the particle nature. And here you'll see it, okay? Ray reversibility means that light retraces its exact path. Okay, its exact path. Now with ropes you can explain this because the rope would follow this whole thing, right? In other words, the atoms are connected from atom to atom. If you move the atoms any way you want to, it doesn't matter. The torsions along the rope that is there already will be always the same. You can move that around, doesn't matter. But see, how do you do it with particles? Particles, if you move this whole thing, especially at the speed of light, well, the particle would not hit the flashlight again. Okay, the flashlight would send it in, right? It bounces. When by the time it comes back, everything already moved in the universe. In fact, you cannot explain with particles. Imagine just the sun twirling around. It spins. And not only does it spin, but every atom of the sun spins and does different things. Imagine now light from the sun sending, straight ahead, all the photons in a straight line, right? Well, as soon as the sun spins, the same atom and the next, they're going to send, the next photon to the side, and then the next one to the side. It would be like a sprinkler system, when you send water around, it would sprinkle in every direction. Light would be always curved. You would never see straight. And that's the problem also with both the wave and the particle. How do you explain it with waves? I mean, a transverse wave, are you bending the wave every time the sun turns around? It just bends or curves the wave? Is it a banana? Is that what the wave is? And then the other thing similar to that is this one, which is the laser ranging experiment that they ran. Well, the only way you can really explain this is if every atom on the moon is physically connected to every atom on Earth. The Earth swings the moon around like, you would swing a ball around the top of your head. And so what happens? The laser pointer, which is connected by electromagnetic ropes to the lunar ranging mirror they've got over there, right? So light can come and go along those ropes, and the moon can go anywhere it wants. Light's not going to get lost because it has a fixed mechanism along which it torques. But how do you explain this with particles? I mean, you sent particles and the moon moved. And then you're supposed to get the rebound, the reflection back to you. That's one problem. The other problem, which I think is a more fundamental problem, when these guys focus their laser at the laser ranging at the mirror on the moon, they already have a problem. Because if light takes a second and a half approximately to reach the moon before it comes back to us, it's 2.5, something like that, seconds round trip, because it's 300,000 kilometers per second, and the moon is like 380. So it takes a little more than a second to go. That means that before you send the laser out, you already have to point to where the moon is going to be 1 second later. You don't point it directly at the mirror. You have to point it further out. And the moon travels 1 kilometer per second around the Earth. So in 1 second, it's 1 kilometer away. So where are you going to point your laser pointer? You can't point it at the laser where the laser is now, because the laser, the mirror, is going to be 1 second later, 1 kilometer away. So you have to point it where the mirror ain't. You got to point it 1 kilometer to where the mirror is going to be in 1 second. So again, a bunch of nonsense to use both particles and waves. The only way you can explain it if there's an attachment, an elongated object rope, right, that interconnects an atom on the moon, anywhere on the moon, the mirror included, to every atom on Earth. Then yes, you can send signals through that rope, in this case, right? And the moon can move anywhere it wants. The signal's always going to go along the rope in a straight line because, the rope is taut. Anyways, I'm going to open the floor up for questions. Anybody have questions? It takes about 10 seconds to receive my message and to get yours back, so just keep that in mind. It's going to take about 10 seconds, and I'll wait a little bit to see if anybody has questions for me today. Could be on the subject matter we covered today, could be on something else. Okay, I do extinction as well, I do other subjects, so you're welcome to ask questions on any subject you feel is appropriate. Give you a second here. What's the best way to learn the ropes? Well, I'll teach you the ropes. Well, the best way is simply, fortunately, the good thing about the rope model, it's illustratable. You can imagine it because you can see it with your eyes. Okay, we're not fooling you here. We're saying, look, light is a rope. And you say, well, what is a rope? Well, it's two twined threads. And you can also imagine it and you can see it because we illustrate it. And we illustrate everything that we do. We can illustrate everything, single thing. Whereas the establishment cannot illustrate a single thing. Not one. I mean, they cannot. What are they going to illustrate for space-time? A fishnet bending? Is that what the 4 number lines are? You know, how are they going to illustrate a particle in 2 places at once? How are they going to illustrate a wave packet? And on and on and on. I mean, you know, you simply can't, you know, space. They say space is filled. Okay, illustrate space. What is space? Don't put any objects in there. Get rid of all the planets, everything. What remains of space? What is that? Is that a physical object? Is that a medium? Does it have something outside of it? You know, and you cannot illustrate anything in the establishment, anything that's critical, crucial, right? The other issue is that not only is it illustratable, but there's another issue as well, and that is that we define the crucial terms that we're going to use in our exposition. So when we give a presentation, a dissertation, we define the key words, and the key words are object, distance, location, exist, motion, etc. We have no use for time, by the way. We don't use time in physics. That's mathematics. We don't use energy. We don't use field. All that belongs to mathematics. We define the words that we need to give a physical interpretation. So the best way to learn the rope model is learn the language. There's like 8 words that form, 8 or 9 words that form the foundations of physics, as we call them. And they're the definitions that we're going to need in order to make our case. And then the whole theory is illustratable. You know, we illustrate everything that we talk about. There's nothing we cannot illustrate because hopefully everything out there in the universe is an object, and an object is that which has shape, and there should be no reason not to illustrate a shape and put it in motion. That's what we do. Okay, what else we got there? You still haven't answered what caused it to bend in that direction. You just said why the frequency decreased. Okay, let me answer that, Wong, there. Yeah, maybe it skipped my mind. When the light comes, first, I hope I made my case that light will go in a given direction because that's, you've cordoned, you've encapsulated light so that it doesn't go sideways. Okay, so I hope that part is clear. Light is now traveling, really it's torquing, right, in the direction in which you've left an opening, a tunnel, right? Now the question is, light comes out now, according to what his question is, it should go everywhere, right? And the answer is, it does. It does go everywhere. Okay, let's get that straight. Light goes in every direction once it comes out. But remember, the main beam, right, to call it that way, the main ray, is straight ahead because you've already kind of chopped it off on the edges when it comes out. So you have this pencil, you know, pointing outwards from your laser pointer. Now, there is light scattering, there's dispersion there, refraction, etc. But that light is not coming to your eye. It's coming to your eyes, but it's at a frequency that you cannot see. So the whole thing, the whole prism is really illuminated. It's all glowing, but it's glowing at a because all the atoms are being vibrated inside the pyramid, the prism. The only issue here is that you cannot see that light. Okay, because again, what's happening, you directed the beam forward, and whatever goes to the side gets lost more and more and more. Those have less frequency, longer wavelength, and it's below the red, infrared part of the spectrum. So you can't see it. But yeah, those atoms are stimulated in every direction. Okay. The other thing that I hope I showed there is that, remember that the light beam that hits the main beam, right, that hits an atom or a molecule actually, is going to refract the light towards your eye, to the atom in your eye. That's connected with a rope. Gazillions of them, by the way, right? So you're receiving refraction sideways. That's why you can see the beam from the side. Okay. If we take the observer out, is there light coming, out of the beam? Of course there is. That means that if it's coming out, it's also going down, it's going to the sides, going everywhere. But in different directions because of the vibrations. Because remember, the way it works under the rope model is light is relayed from atom to atom. The speed between two atoms, the speed is always the same. It's dictated by the letter C. It's 300,000 kilometers per second. Light never slows down or goes faster. It's always 300,000 kilometers per second. The only thing that changes is either the frequency rises and the wavelength link length has to get shorter, right? Or the wavelength gets longer and you have less frequency. Those are, inversely proportional. You can't change that. That's a law of nature. That's how we inherit our universe, right? So you have that already built in there. The only thing that changes is the light that comes to you, to your eyes, has longer wavelength, longer links, right? And because of that, you cannot see it. But the light is refracted throughout the whole prism. Hopefully, every atom in there is being affected by that light. I hope I answered that question to some degree, at least. You're welcome to, if you're not satisfied, you're welcome to put the question again. But I want you to understand that every atom in the prism gets light, gets the torsion, but they all get different frequencies or different link lengths. And the ones you don't see are the ones that are below the visible range. That's all that's happening. Why? Because the main beam is again pointing straight forward. Okay. Now the other issue is the specific angle. That's another question. But I hope you take a rain check on that one. I just want you to understand right now that all atoms in the prism do get torsions. Okay, all of them. Okay, I guess we'll leave it at that, and you're welcome to put questions in writing, and I'll see if I can answer them. You have to try to stump me.